Okay, in this video I'm going to be presenting the notes on plate tectonics. All right, and although it says chapter 9 here, this actually corresponds to unit 4 of what we're studying. Okay, so this whole idea started back in about 1915, and this guy Alfred Wegener proposed what he called this at the time the Continental Drift hypothesis. All right. Although we know this now as plate tectonics, at the time that this was presented, we didn't know anything about the plates, which we're going to talk about in a little bit. All right, and so his terminology was just continental drift. All right, so what was his hypothesis? All right, his hypothesis is that about 200 million years ago. All right, so make sure that you get that in your notes. The MYA stands for million years ago. Instead of having all the 7 different continents, we just had one large, what we'll call a supercontinent, which is called Pangaea, all right, which means all lands. And about 200 million years ago, that big continent started to break up. All right, and so one thing about the Earth is, if you think about it, if there was only one big continent, there would have also only been one big ocean. All right, and the name for that ocean is Panthalassa, all right, which stands for all oceans. All right, one thing to note is that at the time that he presented this idea, it was not widely accepted because all he was saying is that it looks like the continents have been drifting. All right, he had no way to explain why they were drifting. So why did he think that the continents were drifting? All right. So even though he couldn't explain his hypothesis, there were several bits of evidence that gave him this idea. All right. The first is that the continents fit together like puzzle pieces, and I'm going to go through each of these individually. The second is matching fossils. The third is ancient climate and glacial evidence. The last is going to be rocks. All right. So the first bit of evidence was that all of the continents had the appearance of all fitting together like puzzle pieces. All right. And perhaps the most classic example of this is how the east coast of South America looks like it fits into the west coast of Africa. All right. So we've actually kind of pieced together all the other pieces, and it's not just South America and Africa, but there's a lot of other continents that have this similar type appearance of fitting up next to each other. The second big bit of evidence is matching fossils that are found on different continents. All right, so this takes a little bit of time to understand. Okay, so let's pretend that we had a land animal, all right, that lived millions and millions of years ago, but is now extinct. All right. Well, one thing about land animals is they can't swim. All right, or most of them can't swim. So let's say that we had, so this might sound like common sense, but it's not possible for a land animal to swim across an entire ocean. All right. So one thing that they found evidence for is that the fossils, which are going to be the remains of these animals that you find in the rocks, were found both on, today we can find them both in Africa and in parts of South America. All right. And those fossils, if you put the shapes of the continents together, would be in the parts of the continent which would have been right next to each other when these things were joined. All right. So if today these continents are thousands of miles away from each other, separated by an ocean, it raises the question, well, how did the animal get from one place to the other? All right, and the answer is that these continents used to be connected. It doesn't require the animal to swim if there's no ocean between the continents. All right, so this would have been the range of where this animal right here would have lived millions of years ago. All right, and it would have died. It would have gotten buried by the rocks, and once these continents ended up separating, all right, to where they are today, we can now find the same fossils of the same animal here on Africa, but we can also find it here in South America. All right. So this isn't the only example. There's also different types of animals that would be in this range right here, and you can see that the region in South America is directly across from where it would have been in Africa. And so this is the second bit of evidence that we have for continental drift. So the third bit of evidence has to do with glacier evidence. All right, and one thing that we learned in the last unit is that you can tell if glacier, which is a big mass of ice, used to cover an area. All right, you can tell this because it puts scratches, straight line scratches in the rocks. All right, so the interesting thing is, like, when we think about glaciers today, we normally think about really cold regions like Antarctica and up around the North Pole. But today you find evidence that glaciers were in central Africa, all right, places around where the equator is today, where it's actually really warm today. All right, so the question is, how is it that we've got areas today that are that are really hot, really close to the equator, but there's evidence that they were once covered by glaciers? All right, and the reason is that the continents they weren't always in their present locations. All right, back a long time ago, Africa was actually way down closer to the South Pole. All right, and that would have put it in a lot colder part of the world, hundreds of millions of years ago. All right, and so when these glaciers retreated, they left their mark. All right, and Africa moved north towards the equator, and it's now in its present day location where it's nice and warm. But the area, you notice this area of Africa corresponds to this area right here. So the reason that we have it looks like there were glaciers right here is because of when Africa was actually much farther south than really where it is today. And the last bit of evidence has to do with matching mountain chains. All right, you can see here. So what we know from analyzing the rocks is that the rocks in the Appalachian Mountains, which are in North America, are very similar to rocks that are found in mountains in both Britain and in parts of Scandinavia. All right. Well, how can that be if there's a big ocean between them? All right. Well, if you put the continents together the way it's proposed that they existed, you can see that there would have been one long mountain chain here. All right, and when the continents broke apart, that now puts an ocean that separates those mountain chains. But that's why the rocks here are very similar to the rocks over here. They used to all be part of the same mountain chain. So this slide right here just covers some of the major events in the continental drift cycle. All right, so about 250 million years ago, that's when we had all one continent called Pangaea. About 200 million years ago is when there was a big breakup. All right, and so we ended up having two major continents, one called Gondwanaland and another one called Laurasia. All right, one interesting thing about this to note is that even though today India is attached to Asia, all right, notice that a long time ago India was its own separate landmass, which was separate from Asia, and over time India kind of moved northward. All right, and you can see here it's moving closer. So 50 million years ago, it's closer, and eventually it slams into Asia. All right, and that's important because one thing we'll talk about a little bit later is that's the event that eventually caused the Himalaya Mountains, which are the largest mountains on Earth. So as was said before, originally Alfred Wegener, he just suggested that the continents had moved, but he didn't offer a reason for why. All right, the theory that eventually ended up explaining how they moved is what's called plate tectonics. All right, and this is the theory that the Earth's crust is made up of a series of plates that can move and slide against each other. Sometimes the plates can slide underneath each other, but how fast are these plates moving? All right. Well, to give a little perspective on this, the plates move very slowly. They move about 5 centimeters or 2.5 inches per year. All right. And just to give you a sense of about how fast that is, take a look at your fingernails. All right, they're and ask yourself, are they moving? All right, yes, they're moving. They're just moving so slowly that it's very hard for us to notice that. All right, but hopefully you realize over the course of many, many, many years, if you didn't cut your fingernails, they would be. You could tell that they had, that there was a significant amount of distance there. Okay. So it's these plate movements that cause earthquakes, volcanoes, and mountains. Okay, so here's a map that shows the major plates on the Earth. All right, so you can still see the map that shows the continents, but the shaded regions show the plates. All right, so this whole big brown area right here, which includes the entire North American continent, is on the North American plate. All right. The Pacific Ocean has its own plate. That's the Pacific plate. All right. There's this kind of orange region. Notice that the entire African continent is on the African plate. All right. So these plates can move. They can slide under. They can slide underneath each other. They can slide past each other. And we're going to talk about how some of those movements can cause different things to happen. So some of the evidence for plate tectonics, number one is paleomagnetism, all right? And that happens because the rocks align with the Earth's changing magnetic poles, showing patterns of spreading, all right? This can be a little bit hard to understand if you're just looking at a still picture, but essentially, if here is the boundary between two plates, and you've got like in the middle, you've got hot magma coming up and forming new land that pushes these two plates apart from each other. All right, and what happens is that the Earth's magnetic field creates regions where so these rocks right here would all be the same age, and they would have evidence that the Earth's magnetic field was in one direction. But these rocks right here would also be the same age. You can see these pink rocks right here. And the magnetic field there would be pointed the other direction. So you can use that evidence to show evidence for the spreading. Another thing is ocean drilling. All right, if you analyze the ocean sediments, you can see that if there's a region in the middle where the two plates are spreading apart, the sediments this far from the boundary should be the same as the sediments this far from the boundary. All right. Next is earthquake patterns. All right. We'll talk about that just a second. And the last one is hot spots. Okay. So as was mentioned in the previous slide, one of the bits of evidence is the location of earthquakes, and it should also say of volcanoes as well. All right. And one thing that you see is that there's volcanoes basically surrounding the entire Pacific Ocean. They call that the Ring of Fire. All right, and that's because that is the area where the Pacific plate meets a lot of different plates. Okay, another bit of evidence is what's called hotspots. All right, and the most famous example of a hotspot is the thing that caused the Hawaiian Islands. All right, so there's this really hot area underneath one of the plates, and every once in a while, if the area gets really hot underneath the plates, it can actually, some of that magma can end up poking through that plate. All right, and so let's pretend that you've got this hot spot right here, and it stays in the same place. All right, but then you've got this plate that moves over the top of it. All right, well, the thing is that the area on this plate right above that hot spot is going to change its location over time. All right, so this area right here actually got formed when this right here was over top of this hot spot, but it's now over here because the plate has been moving in this direction. So what causes the plates to move? All right, well, we talked before about these things called convection currents, and these are circular ways that the mantle material can circulate. So it gets heated from below, and so the hot mantle rises, and when it gets to the top near the Earth's crust, it moves outward like this over here, and outward like this over here. And that pushes this plate right here that way, and that drags this plate right here in the opposite way. All right, and this just shows again how those convection currents move the plates.